Hey everyone, hopefully everyone had lunch and is, full of energy, no? Apart from the title of this research paper also has hot of burning topics, no? Transformers, stable diffusion, Gen AI. And what we are trying to solve is even more hot. We are trying to address the data deficiency in AgTech, right? We'll also discuss how this could be extended to other domains probably. Now, a quick introduction about myself. Hey, I am Anubhav. I work as an engineer in ML team at iMerit. And I'm here to present a presentation on a research paper titled Leveraging Gen AI with Transformer and Stable Diffusion for Rich and Diverse Dataset Synthesis in AgTech. Now, to give some overview, in recent year, agriculture domain is undergoing a lot of changes, right? A lot of digital transformation, marked by integration of advanced technology to address ranging challenges, right from optimizing crop yields to ensuring sustainable farming practices. Now, central to this entire revolution is the utilization of artificial intelligence, especially generative model, which hold immense promise in terms of transforming the way how we perceive and approach data synthesis in current time. This paper delves into a novel approach of utilizing the power of Gen AI to address a very basic and fundamental issue in AgTech. I'm mentioning about AgTech, but don't take it as an AgTech. This is extended to other domains as well. Now, let's have an introduction around this paper. So we at iMerit have been working on a lot of agriculture-based projects. Now, one thing we found common between all these projects, we have listed few of them. They are scarcity, right? If you go to Google and search for some open source data set, either you won't get it, or they are not up to the mark. In terms of the segmentation, in terms of the labeling of the data sets. And apart from this, there's a lack of diversity in the data set. So let's say you'll have a data set for, let's say, initial saplings, or maybe a tree, or maybe an entire field, but you won't have for the entire life cycle of a plant, right? Now, apart from this, we are trying to address all these issues in AgTech. Apart from this, we'll also try to address the need to have a synthetic data set generation pipeline that could mimic real-world AgTech scenarios. Further, we'll also address the challenges related to data deficiency and data diversity. Now let's have a quick look at the motivation, because we are lazy people, right? A lot of motivation is required to bring us to do something. So let's take an example, right? We are given a use case where we are supposed to train a model. Now the pipeline looks like you are supposed to get the model, get the data, annotate that data, and fine-tune or train your model. Now let's take a decent timeline of 1 week. Now you started with the entire pipeline, you collected that data, you annotated that data, and now you are good with, your model is giving a good accuracy, and now you are done with it, and you are pushing that to production. Now what would happen? In 1 week time, there are a lot of changes that would have happened on the farm side as well. The plant would have grown, the weed would have grown, the density of weed would have grown. Further, it also depends at what time of day you collected that data. Further, there could be a change in the texture of the soil as well, right? So this brings us to a few of the fundamental issues in AgTech, right? That is slow turnaround time, lack of coverage in the data that we collected, right? We can conclude from this example. And there is also a persistent security issue when we collect the data. So people are not easily agreeable to share that data for the farms and all those things, right? Now let's have a context behind our exploration. So how many of you have worked in AgTech domain previously? Just raise your hand. Just a single one? 2, 3. Okay, we have some guys, right? Now one thing you would agree that the data deficiency in the AgTech is something that needs attention, right? Through this paper, we'll address how to have better control over the data quality through synthetic dataset generation. will also address some of the extensive use cases where this could be extended and replicated, right? And apart from this, we'll also see how synthetic data allows us to simulate various combination of crop, various perspective of crops, and different level of density and distribution. So this diagram that you see is the step-by-step process we followed, right? From the identification of data deficiency in AgTech, sorry, I might fall, okay, to synthesizing of, let's say for now, this is just a synthetic data, right? So in the first hand side, in the left hand side, the first block, we collected some data. This data was in terms of we collected few images from the open source data. We web scraped some of the data. Then we utilized this data to fine-tune stable diffusion model. Now this stable diffusion model was then utilized to generate few synthetic data, right? Now this synthetic data was then annotated by an enhanced team of annotators, utilizing an Ango platform, that is iMerit's proprietary tool, but you can use that as well. Now this annotated data was then utilized, combined with the original data, and then this model, semantic segmentation model, was trained on that. Now this entire experiment happened in two iterations. In first iteration, we trained the semantic segmentation model utilizing only the original data that we web scraped and so on and so forth. And in the next data, we combined this synthetic data as well as the original data. Now we wanted to check two things, right? Whether this solution is addressing the issue of data deficiency, that is, since we can synthetically generate in theoretically infinite numbers of images, right? And we also wanted to address whether our synthesized image, does that really mimic the real world scenarios? Now, why did we choose to go with stable diffusion? First of all, it's an open source tool, and that's what we like, right? It allows us to have better control over the parameters, the model architecture, the training loop. Further, there is an ample of documentation and an active community behind stable diffusion, right? Further, we also wanted to make sure this entire experiment could be replicated on a consumer grade graphic card to make it practical and could be used and replicated throughout the industry, right? Now, let's have a look at the synthetic data set pipeline. So on the left hand side that you see, these are all originally collected images, right? These are some of the images were took from the open source data. Some were web scraped. Now these images were then, as I mentioned, was utilized to fine-tune stable diffusion model. This stable diffusion model then synthesized these images, the images that you see on the right hand side. Now, if you conclude through this slide, two things we are directly addressing, right? It is the diversity and the deficiency in data. Now, the main power where the power of Gen AI kicks in, right? You see the pots, the white pots, cotton pots, right? These were not at all in the original data. These were just created somehow by the stable diffusion model, right? And this is, we were even surprised to see whether this model could even synthesize these that we have even not put in the training data as well, right? Now Dino V2, this is a, I think most of you would be familiar with the Dino V2 architecture, right? We use this standard model to fine tune and quantize our this synthetic data. Now, how many of you are familiar with LoRA algorithm? Few of them, okay, fine. So you should try this, right? So we utilize LoRA module to fine tune this model. So how does this, what does LoRA module do, right? It's a local rank adoption. You can search through on Google for the in detail thing. But this provided one of the benefits, right? It enhances the efficiency through faster fine tuning. So the entire experiment was replicated even faster utilizing this particular algorithm. For quantizing of this model, we utilized mean IU, that is the industry standard matrix, to quantize the localization model. Right? What is mean IU? Mean IU is basically average of IU that is calculated across multiple classes, multiple samples. to put a proportionality relation between the mean IU, just for whoever is not familiar with mean IU, to put a proportionality relation, the higher the value of mean IU, the better the model would be performing, right? This is a general thing. Now on the right hand side that you see, these are the training graphs. The orange one corresponds to the model that was trained on the original data without including the synthetic data. While the model, the blue line that you see, the blue graph, that is for the model that was trained on original plus synthetic data. Now, if you compare both the graphs, right, you can easily conclude that the addition of the synthetic data to the original actually helped us in training, right? It converges better, it attained better metrics. Now, we also wanted to make sure that this is not, it would also work on the original data as well, right? So we curated few datasets as in test datasets. We utilize similar process, right? That we curated training data. Now, when we compared the metrics, the model that was trained just on the original data attained around 76% mean IU, while the model that was trained on synthetic plus original data attained around 84% of mean IU. Now, what can we conclude from this? There are two things, right? First of all is that the synthesized data really mimic the original data, right? And since the metrics are high, now to put some numbers in this, right? We utilize just 600 synthetic images. Now, the model performed better, so we can conclude, right? The synthetic data was performing better. Now to have a glimpse on the results. The first column corresponds to the images from the test data. I'm using indexing, sorry. The second column refers to the humanly annotated data, right? These are mass generated by human annotators. The third column corresponds to the model that was trained just on the original data. And the last column corresponds to the model that was trained on synthetic plus original data. Now, if you compare the results, right, between the original and the synthetic data, you could easily conclude that the model that was trained on synthetic plus original data had better results in terms of the pixel accuracy, in terms of the boundaries, or in reduction of noise as well, right? Now, conclusion and broader impact of this experiment. This method described can be used in particular to AgTech. This could be utilized to generate various perspectives, probably some crop types or a combination of crops, etc. Further, this also makes sure that the generated data is realistic and closely correlates between the your data in the wild, right? Further, this could be extended to other domains. We have specifically trained this on AgTech data, but this is easily extensible to other data as well, right? Now, in conclusion, our journey through Gen AI, Transformer, and Stable Diffusion has revealed a tapestry of innovation, just some chat GPT words. And yeah, we are pretty, sure that this inclusion of this transformer would completely change how we approach and how we approach a data synthesis task today. That's all from my side. Thank you. I would also like to mention my co-authors. Are they? Savanan, Devakar, and Abhishek. Thank you for accompanying me. I'm ready to have any questions.